Hello, my name is Guy and I'm going to talk about formal methods with a touch of magic. This is joint work with Pana Darizadeh, Tom Hansinger, and Anna Lokina. This work is part of a recent effort to combine formal methods and machine learning. The reason that this combination is so natural is because these two fields have complementary benefits and drawbacks. In terms of benefits, formal methods aims at the worst case. It gives us worst case guarantees such as finding corner case bugs or showing that they don't exist. Machine learning, on the other hand, aims at the average case. It gives us unparalleled performance, superhuman performance at times. In terms of drawbacks, the main drawback in formal methods is scalability. We can scale to huge systems, definitely not as big as in machine learning. Performance is also a drawback. Performance traditionally is not considered at all in formal methods, and only recently it has received a lot of attention. But still, studying performance in formal methods is at its infancy. In terms of drawbacks of machine learning, first of all, it doesn't give us worst-case guarantees, and second of all, models that are learned are typically unexplainable to humans. So the combination of these two drawbacks leads to us to untrustworthy systems. And this is a real problem when we want to deploy these systems in practice, especially when we're talking about safety-critical systems, for example, self-driving cars. We want these systems to be provably correct or predictable at the very least. I mean, a human driver would be okay if his autonomous car would say, "I don't know what's going to happen, please take the wheel for now." But unfortunately, learned systems are neither correct nor predictable. And in this work, we're trying to add ideas from formal methods towards getting correct and predictable systems. We're going to focus on the controller design problem, where I'll describe it abstractly. So a controller is a device that interacts in an ongoing manner with a plant. In each point in time, the plant outputs its state, and the controller produces an action. Then this action updates the state of the plant, and it produces a new state, followed by an action, and so forth. So controllers are all, we can find controllers everywhere. They can control cars, elevators, they can control robots or drones, and can even control games. In a game, the plant outputs a state on the screen. For example, in Pac-Man, we see where the Pac-Man is here. It's a Simpsons game, and our actions in return are moving Bart. He can move right, left, up, or down, and so forth. The holy grail in controller design is a framework that is both scalable and produces controllers that are correct, perform optimized performance, and make explainable decisions. In this work, we're working towards this holy grail with a combination of techniques from these two fields, where on the machine learning side, we're focusing on reinforcement learning, which is the standard technique to design controllers in machine learning. So in reinforcement learning, there are basically two phases. First, there is an offline training phase where the agent basically randomly explores the plant. Think about a robot that is placed in the middle of the room, and it cycles around the room to understand where it's being deployed. So this starts off by feeding completely random actions to the plant, and the plant outputs for each action that it gets, it produces a state as well as a reward. And the agent learns by maximizing the expected rewards. So, for example, in the robot scenario, we might give the robot a reward when it picks something up, and give it a larger penalty when it hits the wall. And eventually, we hope that the robot learns not to avoid walls and to pick up things that it is supposed to pick up. So once offline training is concluded, we move to the second phase, which is called deployment. Here, we deploy the controller that controls the plant, as I described just a minute ago. One thing I would point out here is that at the deployment stage, the controller is not changing anymore. And now you might wonder what happens if at the deployment stage, the controller observes a state that it did not see during training. And there's unfortunately no good answer to this question. The answer is that this is where unexpected behavior comes in. And one of the things that we ask in this study, in this work, is can we use insights that are learned during training even in a changing environment? And we will answer this question towards the end of the talk. Reinforcement learning has made a quantum leap since the introduction of neural networks into the process. This is called deep reinforcement learning. It was initiated in this paper from 2013, and basically, the deep reinforcement learning is the same procedure I just described. Only the agent is represented using a neural network. Homer here would be a neural network. So the output is a controller that is represented using a neural network. And since we're going to have all kinds of controllers in this talk, we're going to call the output of DeepRL the wizard. So the wizard is a neural network, which we assume optimizes plant performance because it's trained using deep reinforcement learning. But because it's a neural network, we treat it as a black box. Neural networks are known to be complicated and hard to read. So we say that this wizard does not reveal its internal decision procedure. What we're not going to assume is any guarantees on the training. So now moving to the formal method side, reactive synthesis is the standard tool in formal methods to design controllers. Broadly speaking, the problem is the following. Given a specification phi, typically as an LTL formula, find a controller that ensures that the plant is correct, that it satisfies the formula. And what you should immediately be pointing out here is that there is no performance considerations in the standard definition of synthesis. So this is where we stand. Synthesis gives us correct by design controllers, whereas DeepRL gives us controllers, wizards, that optimize average case performance of the plant. And the question that we ask is how to get the best of both worlds. So the way we go about this is that we think of the wizard as this oracle in terms of performance, and we're taking advice from it. And now our synthesis procedure is going to synthesize a correct by design controller, but one that follows the wizard's advice as closely as possible. Now we hope that since the wizard is good at achieving good performance, that our synthesized controller will also be good at performance, and not only be correct by design. But there is a problem with this plot, and namely that the wizard is a neural network. This is a huge and complicated object that uses complicated operations, and synthesis and scalability in synthesis is already a bottleneck, and including such a complicated object into it is simply out of the question. So how do we go about it? How can we achieve this plot? And the idea, which to the best of our knowledge is novel in the context of synthesis, is the following. We extract a model, which picturestically speaking we call the magic book. Think of the wizard as this oracle in terms of performance. Well, the magic book is supposed to be the recipe according to which it's making its decisions. This is supposed to reveal how the wizard is making its decisions. More technically, it's supposed to be a good approximation for the wizard as a function, and it's supposed to be small and simple enough for formal methods to deal with. Now, the reason that we even hope to achieve such a thing is because it's a standard procedure in machine learning. This is called distillation in machine learning, and I list here only 2 papers, but there's plenty of papers on the topic. So the first thing we are going to do is use a magic book in synthesis. We're going to use it as a proxy for the wizard. We're going to get advice from the magic book, synthesize a correct by design controller, one that follows the magic book's advice as closely as possible. And then we're also going to do bounded model checking based on the magic book. This will be at the end of the talk. But first, let's talk about magic books. Our model for magic books is called a random forest. Recall that the wizard is a neural network controller. So the wizard is a function from planned states to actions. And so the random forest is the same thing. It's a function from planned states to actions. And the way this operates is the following. A random forest is a collection of trees. Now, each tree, given a planned state, produces a vote, where the way this works is that each internal node of the tree contains a predicate over states, and each leaf is labeled by an action. So, given a state, we get a unique path in the tree that ends in a leaf, and that gives us the action. So the tree votes for an action, and each tree votes for one action. The random forest outputs the action that got the most votes. So this is how this model operates. How do we obtain such a model? Well, we run the wizard with a plant for a long time, say 1,000 or 4,000 time steps, and this gives us a large data set of state action pairs. So at state S1, the plant outputs action A1. At state S2, the plant outputs A2, and so forth. And once we get this data set, we train a random forest using standard techniques. So at this point, you should ask, well, this is nice, but does it work? How does the magic book compare with the wizard? So we tested this experimentally. We looked at the following case study. We have a taxi that travels around a grid, a 10 by 10 grid, and it collects 3 passengers. So we give it, the wizard is trained to collect as many passengers as possible at a 1,000 time step frame. And whenever a passenger is collected, it reappears at a random location on the grid. So comparing so here we have a comparison between the average number of passengers that the wizard collects, a magic book which is a decision tree of depth 10, so one decision tree of depth 10, then a random forest with 5 trees each of depth 6, and the last one is called extreme gradient boosting with 100 trees of depth 10. And as you can see, in all of them, the magic books perform very well. Here is a movie that shows the magic book on the left with 5 trees of depth 7 performing very well compared to a wizard that collects passengers. So we say that this is good news. We have a good approximation for the wizard, and it's definitely small and simple enough for formal methods. Now we can use it. So the first application is in synthesis. We construct a game based on an abstraction of the plant that is given by the user. For example, we can disregard the passengers completely. So each black dot here represents a concrete state in which the taxi is placed on position 2, 2, 3, and disregarding the passengers completely. So I'm going to describe the game with a magic book with one decision tree, and it extends to a random forest. The first player is the adversary. It chooses a path in the tree. So a path in the tree gives rise to a subset of states. Exactly the set of states that gives rise to these paths, to this path when we feed them to the tree. So think of this as the adversary choosing a subset of states in which the plant can be in. He reveals a subset of states in which the plant can be in. Now comes our protagonist, Homer, and he chooses to accept or reject the adversary's action, where the action is A here, the action that's labeled at the end of the path. If he accepts the advice, he gets a reward of 1 and updates the state of the plant. And if he rejects the state, then he gets a reward of 0 and again updates the plant. So what I described here is the game arena that we construct offline. We solve this game, which means we find an optimal strategy for Homer, and this is our controller that we output. So note that Homer's strategy is a function from states to actions, which is exactly what we want. So let me tell you a bit about the experiments that we did. We considered the following specification: collect as many passengers as possible at 1,000 time step frame, and correctness is visit a gas station every 40 time steps, a gas station that was not present in training. So here is a movie of our synthesized controller. As you can see, it's picking up passengers and going to the gas station when the time is out. Putting a bit of numbers, so you can see that the average number of passengers that is collected is comparably high, especially if you take into account that the wizard and the magic books are not visiting a gas station every 40 time steps. So we again think this is good news. We managed to find a correct by design controller, correctness being visit the gas station every 40 time steps, and it achieves very good performance just by following advice from the magic book. But we want to do more. One of the goals of this work was to open up the black box wizard. And to show you that we did manage to achieve this, we're going to compare with a line of work which is called shielding and is promoted by Roderick Bloom and his student Bettina Könighofer. And if you're interested in shielding, I encourage you to look at Roderick's keynote presentation at Concur only a few weeks ago. So what is shielding? The idea is the following. And each point in time, the plant outputs its state to a controller. In this case, it's the wizard, but this doesn't matter. It's a controller. And the controller feeds it back an action. Now, the shield is a proxy for the wizard. Every time the wizard outputs a state A, the shield observes the state, monitors the state, and can change it before it gives it to the plant. So this is sometimes called an enforcer. The idea is that worst-case guarantees are given by the shield. For example, in their first work, they studied shields for safety specifications. If the action A here was not a safe action, then the shield can change it to a safe action A prime. Later on, we studied together with them shields for performance specifications which generalize liveness specifications. But in any case, both works assume that the wizard is a complete black box. The shield treats the wizard as a black box. And the question that we ask is, can we do something that shields cannot do? And to answer this, we add a wall to the grid, a wall that was not present in training, and the specification we look at is the same as before, only now we require the taxi not to hit the wall. So now what you're seeing here is the wizard combined with a shield. The wizard knows only about the places of the passengers, and the shield knows only the position of the wall and the gas station. So it ensures that the taxi visits the gas station every 40 time steps and does not hit the wall. But when the wizard tries to collect a passenger to the left of the wall, it's making an unsafe action. It's going to hit the wall, and the shield is changing it, is overriding its action and choosing some arbitrary action instead, since it doesn't know about the position of the passengers. And this arbitrary action is not enough for crossing the wall. In comparison, this is our synthesized controller, and as you can see, it's happily crossing the wall. Let me just point out that this is not a cherry-picked movie. We see this behavior repeatedly. What you're seeing to the left is the numbers that are coming out of the synthesis game solving. What's going on here is that the controller is directing the taxi to places where the magic book is very certain about its actions. And fortunately enough, this happens around passengers. So this is why it's managing to cross the wall. So I'm particularly happy about this experiment because what we see here is that our controller is managing to get insights using the magic book that were learned in training, even in a changing environment, an environment with a wall that was not present in training. Right, so let me sum up this part of the talk. We use DeepRL to train a wizard. We then extracted a magic book, which in our case is a random forest. We then combined it with synthesis to produce a correct by design controller that has good performance. In the paper, you can also see another application of the magic book in synthesis, namely in multi-agent synthesis. In the last part of the talk, we're going to combine the magic book with bounded model checking. Bounded model checking is the problem of finding a trace of length k being a parameter that satisfies a given specification. The idea is that using bounded model checking, we're going to make the wizard more predictable before outputting it as the controller of the plant. Specifically, we're going to look at two applications of bounded model checking. One is called verification, and the second is explainability. Using these two applications, the designer could get insights which he can combine in a secondary training to make the wizard, again, more predictable. So I will quickly describe how we reduce bounded model checking to SMT solving. The states of our plant are tuples that contain the position of the taxi and passengers. So we construct variables, state variables we call them, one for each time step. So an assignment to these variables is supposed to be a path of the plant under the control of the magic book. We also have actions. This is the action at time. You should read this as the action at time I. And we have the following constraints. So first we have basic constraints that constrain the fact that each state variable is indeed a state in the plant. For example, positions should be on the grid, or passengers and taxis can't share the same position. Then we have path constraints, which guarantee the fact that if an action is chosen at time I, then the state at time I+1 is adjacent to the one at time step I. For example, when right is chosen at time j, then the taxi should move right at time j plus 1. Another example is if a passenger is not collected, it stays in place. The most interesting and important constraints are the ones that guarantee that action A is chosen at time I. For that, we need to simulate the execution of the random forest. And I'm not going to dive into details here, but basically we have a constraint for each path in the forest. When this is a decision tree, we only need these set of constraints. But when this is a forest, we also need summation to simulate the fact that there is a voting taking place. Right, so this is a sketch of the reduction from bounded model checking to SMT, and now we use it first in verification. So the goal in verification is to find counterexamples of the wizard controlling the taxi. For example, for the specification, never enter a loop without collecting a passenger. What you see here is a wizard controlling the taxi and getting into the loop. The way we obtain this example is running BMC for magic books, getting a counterexample for the magic book, and checking if that counterexample is also a counterexample for the wizard. Fortunately enough, because the magic book and the wizard are close, many of these examples are indeed counterexamples for the wizard. Next, in explainability, the goal is to explain the operation of the wizard to a human designer. One way we can do this is to find interesting traces. For example, this trace is suspicious because the taxi collects the passenger that is not closest to it first. A second thing that we can do is collect a large and interesting data set. For example, in this data set, when the plan starts off at state S1, Lisa is going to be the first passenger to be collected. At state S3, Bart is going to be the first passenger to be collected. So we can use our bounded model checking procedure to collect this large data set of traces that correspond to the wizard controlling the taxi. In this table, we show that this approach is indeed scalable. For example, here, what you see is the time to find a trace where we amortize over 250 traces. So this is 44 seconds when, sorry, this is less than a second when the bound is 9. The length of the traces are 9, and we're amortizing over 250 traces. The second thing that you see here is what percentage of the traces are shared between the wizard and the magic book. And as you can see, this is very, very high, also in quite large bounds. So once we obtain this data set, we can construct a human interpretable model. This is a very, very small decision tree that aims at explaining how the wizard is making its decision, which passenger is it going to collect first. This brings me to a bit of related work. So first of all, I mentioned that this table shows that our approach is scalable. We can collect a large data set of wizard controlling the plans. What the disadvantage of our approach is that it's not sound. When our bounded model checking says that there is no traces, the only thing that we know is that the magic book, that there are no traces for the magic book test. If we're talking about verification, the magic book is correct. We don't know anything about the wizard. For that, wizard-based BMC was studied in this work. This is the only wizard-based BMC that we know of, and they designed a custom-made tool. We, on the other hand, use Z3, which is a standard tool, and we actually implemented wizard-based BMC in Z3, and it was incapable of solving the ridiculously small instances. Another related work is two works that implement a magic book-based BMC similar to us. The nice thing about these works is that they consider a case study which is very different from us. This supports the claim that extracting magic books is not restricted to our case study, rather it's a general concept. So this brings me to future work. Again, the most interesting questions, I think, the most interesting immediate questions to ask are on the extraction of a magic book. In which other domains can we find magic books for wizards? And maybe more importantly, can we find magic books with guarantees? Second of all, we studied a combination of formal methods and machine learning and reinforcement learning in particular. We only made a stab at this problem, and we think that there is much more to do in getting the best of both worlds. With that, I will conclude.